Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we're going to continue our discussion of single degree of freedom oscillators with a focus on the topic of mechanical resonance. We're going to consider a harmonic oscillator as shown here with an external force applied to it in the form of a F times cosine of omega t. The equation of motion is shown here. And again, the solution to this is a summation of a transient and a steady state response. And I've gone ahead and drawn what those would look like on the left, on the right here as well, here. So we're not providing any initial conditions here because we're going to focus on the steady state response only. So we're going to consider our steady state response, which is that, let me scroll up here, so x of ss of t is equal to some big X times the sine of omega t minus theta, where big X is equal to the forcing amplitude F divided by omega times the square root of b squared plus the quantity k divided by omega minus m omega, that quantity squared, and the phase theta is equal to the inverse tangent, or you could say the arctangent of k divided by omega minus m omega divided by b. What we're going to do now is we're going to consider equation 37, and we're going to bring in omega into the square root, which will then give us the following. We'll have that x is equal to the force, big F, divided by the square root of b omega quantity squared plus the quantity k minus m omega squared quantity squared, and that is the end of our square root. From here, we're going to multiply both sides by 1 over m divided by 1 over m, and that is equal to 1, so it won't affect the left-hand side, but we're going to use that on the right-hand side. So we're going to get that big X will be equal to the quantity F divided by M divided by the square root of B divided by M times omega, that quantity squared, plus omega 0 squared, our natural frequency, minus omega squared, and then that whole quantity squared. The benefit of writing it in this form is the quantity that I'm now underlining. This is equivalent to 2 times beta times omega. And just for reference, beta was equal to b divided by 2m. So from here, we're going to end up with that our displacement, which is a function of omega, its amplitude is going to be equal to F divided by M times divided by the square root of 2 beta omega quantity squared plus the quantity omega 0 squared minus omega squared quantity squared. What we're going to do now is we're going to divide by the forcing amplitude. And so we're going to call this H of omega is equal to X of omega divided by big F. And that's equal to the quantity 1 divided by the mass divided by the square root of 2 beta times omega quantity squared plus omega 0 squared minus omega, and then omega should be squared, quantity squared. And this is known as the frequency response function, or FRF. So if you ever hear someone talk about an FRF, this is what they're talking about. This idea can also be extended to multi-degree freedom systems, but we're not going to cover that in this class. All right. We're going to consider the case where we have no damping, and in that case B is going to be equal to 0, and then we'll find that x of omega will simply be equal to F divided by M divided by omega 0 squared minus omega squared. And then I want you to take a moment, look at this equation, and see if there's anything that might alarm you about this equation, as particularly what can, think about how the response can be and how it can grow. Pause the video and take a moment or maybe a minute to think about this and try and see if you can figure out what might be a problem in this case. Okay, if you haven't managed to figure it out, then ask what happens when omega is equal to omega 0. And in that case, pause the video and think about what would happen in that case. Okay, so in the case when omega is equal to omega 0, we will get that x is equal to F divided by M divided by 0, meaning that the response will go to infinity. That is, our displacement amplitude blows up and goes to infinity. So, of course, this is not going to happen in a real structure, but what this implies is that there's going to be a very large amplitude. And in real life, what will happen is the structure will end up breaking before it achieves an infinite displacement, which is bad either way. So with that in mind, this is what the concept of resonance is. Resonance implies that if without damping, if you force at the natural frequency, the response amplitude goes to infinity. That is what a resonance is. And it's, in a sense, a feedback loop where the displacement response grows over time rather than settling into a constant amplitude. With that in mind, how do you think the damping affects that response under the condition of resonance? Take a moment and pause the video and think about what that could mean. What does the damping do to that? Will you still get an infinite response, or will you get something else? Okay. With that in mind, we're now going to take a look at what damping actually does to the system. So let's just recall that our steady state amplitude x is equal to F divided by M times the square, or divided by the square root of 2 beta omega, that quantity squared, plus omega 0 squared minus omega, that should be omega squared, quantity squared. And in this case, if omega is equal to omega squared, then we're going to cancel out that second term in the square root, but we'll be left with the first term. And so in this case, we can find that big X is equal to F divided by M divided by 2 times beta times omega, which would still be omega 0, but this is now less than infinity. So in that case, we can see that the damping prevents the response from growing without bounds, as in the undamped case. So introducing damping prevents us from achieving a large or an infinite displacement. That doesn't mean that the amplitude is small. In fact, even at resonance, the amplitude is going to be very large when you force at resonance. In fact, we can compute the maximum displacement when that denominator is maximized. So F and M are both fixed, and that means that we're going to find the maximum displacement whenever that denominator is minimized. And by doing that, we can find the frequency at which we get a maximum displacement. We can see how that compares with the natural frequency as well as the damped natural frequency. So in that case, the denominator, let's call it big D, is going to be equal to the quantity 2. In this case, we can remove the square root. So 2 beta omega quantity squared, because the square root of a small number is going to be still a small number. So in this case, that quantity squared plus the quantity omega 0 squared minus omega squared, quantity squared. And we now want to find when this quantity is minimized. And to do that, we're going to take the derivative of big D with respect to omega in this case. Doing so, we'll get the following. We'll find that dd over d omega is equal to 8 beta squared omega minus 4 omega times the quantity omega 0 squared minus omega squared. And that is the derivative. So again, d is minimized when its derivative is 0. That tells us, and we can actually pull an omega out, so let's do that. So we'll get omega times 8 beta squared minus the quantity 4 times omega 0 squared minus omega squared. That must be equal to 0. So from here we have two options. First, omega could be equal to 0, in which case that equation would be satisfied. So if omega is equal to 0, that satisfies it. In this case, we actually get what is known as the static force. So the static force, or a static force, represents a local minima for this response, or local maxima. The other option is for everything inside the parentheses, and this is 8 times beta squared minus 4 times the quantity omega 0 squared minus omega squared. That must be equal to 0. We can solve for this, so let's just say solving for omega. We get the following, that omega must be equal to the square root of omega 0 squared minus 2 beta squared this time. So in this case, the maximum displacement occurs at a frequency that is less than both the natural frequency and the damped natural frequency. So damping actually shifts the resonance back. So one thing I'd like to do briefly is just to draw what that frequency response function looks like in a graph. So on the horizontal axis, we're going to have omega. On the vertical axis, we're going to have h, or that frequency response function of omega. So for the undamped case, I'm going to do that in blue. We're going to start at some static value, some non-zero force, and it's at, jumped a little bit ahead here, but at omega 0, that response is going to grow to infinity, and then it's going to drop, and it's going to end up leveling off. Now when we add damping, we just saw that it's going to be, that peak is going to be shifted a little bit. I'm not necessarily going to be able to accurately draw this, but I want to show what happens when you increase the damping. So when we have damping here, we're going to peak just a little bit before, and we're going to come back down and converge like that. So as we increase the damping, the location of that peak is going to shift. Let me redraw that. The location of the peak is going to shift, and the amplitude is going to get lower as well. So this is the direction of increasing damping. Oops. All right, and that's everything we want to say about mechanical resonance in this lecture.